Swayam Prabha. Digital India. Educated India.
Welcome. So, in our second lecture of the week 2, we are discussing the elements of calculus of variation. So, here in the last class we have introduced functional and then introduced what is the Euler-Lagrange equation by using some of the classical calculus of variation problem, which is the Brachistochrone problem. So, with the help of Brachistochrone problem, we have found out the Euler-Lagrange equation. Now, here in this lecture, we will extend that and we will recapitulate a bit, and then we will solve one. We will try to solve one problem with this knowledge. So, what we have learned in the last class is this, that we have solved one simple problem from point 1 to point 2, the Brachistochrone problem, which actually is this, and then the approximate paths, approximate functions, or the any other forms are something like this. So, this problem we have found out how to construct a functional. For instance, the functional for this Brachistochrone problem is something like this. This I integral of x1 to x2 1 plus y prime square by 2gy to the power half dx, where y prime is dy dx. Right now, we also instead of choosing this, what we did essentially, we write a functional of this form, that is integral x1 to x2 f of x comma y prime dx. So, now we use this condition, that is di tilde by d epsilon at epsilon equals to 0 is 0 to minimize this functional. To do that, what we did is we approximated y, or y tilde we write in this form, that yx plus epsilon into eta x. Now, eta x has to be the admissible function, or in other sense, that y tilde x has to be the admissible function. So, what do you mean by the admissibility? For this problem, that we know y at x1, that is 0.1, and y at x2 at 0.2. So, the admissibility condition for this approximation has to be that eta of x1 and eta of x2 has to be 0. Now, so we converted to a scalar minimization and simple Taylor series. We use simple Taylor series to find out this function, to find out the optimal criteria. This. Now, from this, what we have found out is that our Euler-Lagrange equation looks like this: del f by del y minus d dx of del f del y prime equals to 0. So, for all eta x. Now, for all eta x means it is admissible eta x. So eta x cannot be arbitrary, because again I am reiterating this, because eta x has to be the boundary condition it has to satisfy. Now let us see some other problem, or specifically that what happens to the our structural engineering problem. So let us see some problem which is related to structural engineering. Suppose there is a bar, okay, the bar problem we all know very well. So this is a bar. So suppose this bar is loaded with a load like this, so axial load, but distributed axial load, okay. So let us say this axial load is q, okay. It can be a function of x, so it can be a function of x, or it can be a function constant also. So this, let us take this bar is area is a, this also can be a function of x, e, and then length l. So length is the constant, let us say. Now a can be variable, so in case of a tapered cross section, a can be a function of x. Young's modulus can also be variable. So now we know what is the strain energy density for this bar. So the strain energy density of this bar we know is integral 0 to L AE by 2 dw du, so dx whole square. So how we get this strain energy? So it is very simple, because we know that strain energy of a one-dimensional body is something, if it follows the linear elastic material, then the area under this curve. So naturally area under this curve means suppose this is my epsilon axis, this is my sigma axis, so this is my the area if I take, so this is the area, so half of sigma into epsilon. So sigma is again your E into epsilon, so E into epsilon square. So now what is E? So E is the Young's modulus, and epsilon is the strain. So I can write it du dx whole square, right? So now again if I write this, then I have to integrate, right? So now this is the density. Now integration obviously has to be the over the three-dimensional space. So in the three-dimensional space, area integral will be just in area, so I just write it A. So this is my strain energy. So now area volume integral becomes line integral. So this is my strain energy. Now what is the potential energy for this bar? Now with this load, because the potential energy will be my phi integral 0 to L A by 2 du dx whole square dx minus your the work done by the force q. So naturally this is also q into qx into u. So ux, u is a function of x, remember that it is not a constant u. So what is u? U is the displacement in this direction, or the x direction. Now this is a 1 degree of means at each point there is 1 degree of freedom, only axial deformation. So this is a bar problem, right? So bar. Now if you look carefully, that this is very similar to the functional that we are talking here. So if I had to if I had to now apply this theory here, then what will be my case? So suppose this is my phi, then if I just write its Euler-Lagrange equation, so this is known as Euler-Lagrange equation, that in the last class we have found out. This is Euler-Lagrange equation. Now this Euler-Lagrange equation for the bar case, how we can find out? So the first quantity is del f by, so what is our f? So first let me write it, my f, in a proper manner. So that is a by 2 del u, not del u, so it is here, it's a du dx whole square minus qu into dx. Now this is my f. So if I look carefully, this is my f compared to this, right? Now this f, I want to find out its Euler-Lagrange equation, or the functional, the integral expression of the functional. So now I want to find out its Euler-Lagrange equation. How should I find out this Euler-Lagrange equation? So I just let me substitute. So if I here f is actually this and y is actually your u. So naturally, if I had to find out partial derivative of del f del u, then this will be this. So which is half will go. So a e du dx. So this is my partial derivative of this thing. Now if you look, if you do this, then this is wrong, because this is a partial derivative. So here, so that's why it is important to write these functional here in this form. For instance, integral 0 to L, this is nothing but a e by 2 u prime square minus q u dx. Now you see, u prime and u both are variable here. So u prime is actually your derivative of u. So that's why it is a partial derivative. Now naturally, del f by del u will be your del f by del u will be your qu. So this term. So naturally it will be minus q, right? So q is a function of x. So this is my del f by del u. So assuming that this is f. Now the second term, that is del f by del u prime, is my this. So this is nothing but a u prime, right? So now if I write it, so a e du by dx. Now if I just wanted to write my Euler-Lagrange equation, so let me again write my Euler-Lagrange equation expression. So Euler-Lagrange equation is this, that is del f del y minus d dx of del f del y prime equals to 0. So now substitute this. So after substituting, I will get del f del u. So Euler-Lagrange equation for the bar is this, that is del f del u minus d dx of del f del u prime equals to 0. So if I substitute now, this is nothing but q of x minus d dx of a du dx, right? So this is equals to 0. So now if I take the a and e are functions of are constant, so it's not a function of x, then I can write this thing as ae d2u by dx square equals to plus q plus q equals to 0. So this is my Euler-Lagrange equation. Now this Euler-Lagrange equation is essentially the governing equation of the bar that we all know, right? Because this is a governing equation of the bar. So how to get the governing equation of the bar? That is through the Euler-Lagrange equation. Now the governing equation is not all about this differential equation, rather it is included. The governing equation means the differential equation is invalid without boundary condition. So what is the boundary condition? So now if you have remembered our previous class, while deriving this we had a boundary term also. So let me rewrite that thing here again. So the boundary term, if you look carefully, that boundary term for del f del y prime into eta of x, it was at x equals to x1 and x equals to x2. This was our boundary term. So we made it 0 because eta of x1 was equals to eta of x2 equals to 0 for the Brachistochrone problem. Brachistochrone problem. But for this problem, the bar problem that we are doing here, what is my boundary condition? So boundary condition is at this point, that is at x equals to x1 or 0. So at x equals to 0, what is my boundary condition? That is my u is 0, right? And what will be here my boundary condition? The boundary condition here will be my so here if you look carefully, there is no displacement specified. So naturally the force boundary condition will be there. So the force boundary condition will be AE del u del x is 0. So what is the meaning of this? The meaning of this is coming from the theory of elasticity, that is sigma dot n is 0. That is sigma dot n is the outward normal, is unit normal is 0. So now this is my sigma. So A du dx is my sigma. So du dx is epsilon. If you look carefully, that is du dx. So it follows the Hooke's law. The area is actually the integral, so it is over line, so that's why. And n is the unit normal in this direction, so which is x direction, so which is 1, so that's why this quantity must be 0. So this quantity is the sigma dot n. Now this quantity is 0. So here this is the boundary condition. So if you look carefully, this is the displacement boundary condition, while this boundary condition is the force boundary condition or the derivative boundary condition. So this type of boundary condition is known as Dirichlet boundary condition. Dirichlet boundary condition, and this type of boundary condition is known as the Neumann boundary condition. Neumann's boundary conditions. So this is also known as the kinematic boundary condition. There are several names. So kinematic boundary conditions. This is also known as the force boundary condition. So all those things are there. So now you see again our admissibility criteria, if you look from the here, that this was the admissibility criteria for my Brachistochrone problem. But for here the admissibility criteria is little bit different. So that means that is eta x, or this function is actually specified at x equals to x1, which is 0 here. So now eta x is not specified. Eta x cannot be specified at x equals to x2, or it can be arbitrary at x equals to L. So because if the bar problem, that means this at this point at x equals to 0, our u is 0 given, but at x equals to L u I don't know. So naturally, one of them, naturally I have to specify this condition. Otherwise, this is not applicable. So what is this condition, del f del y prime? So if you look carefully, that del f by del y prime is my this. So this quantity is 0 given. So naturally these two quantities will go to 0. So what will be the complete differential equation for the bar problem? The complete differential equation will be AE d2u dx2 plus q equals to 0 and u equals to 0 at x equals to 0 and AE du dx equals to AE du dx equals to 0 at x equals to L. So this is for all x from 0 to L. Now this is the complete differential equation or the Euler-Lagrange equation. So if you look carefully, that this functional minimization also leads to the boundary condition of the physical system. So there are two types of boundary conditions we observe, that is one Dirichlet boundary condition or Dirichlet boundary condition, another one is Neumann boundary condition or the force boundary condition. Now this is actually involving, the Neumann boundary condition is involving the derivatives of the problem, while Dirichlet boundary conditions are involving the field variable u. So this is the Dirichlet boundary and this is the Neumann boundary. So here that is sigma dot n is 0. So that means A du dx is 0. So this is the Neumann boundary. So there are another type of boundary conditions you may encounter, but we will not discuss about this in this course. That is the Robin boundary condition or the mixed boundary condition, where the field variable and as well as the derivatives of the field variable are involved, or the combination of field variable and the derivative of its are combined together to have a boundary condition. For instance, in case of a wave propagation and the seismic ground wave propagation or seismic wave propagation, we find out some kind of this kind of boundary condition, and there are other in electromagnetics also this kind of boundary conditions are involved, but we will be mainly discussing this kinematic and force boundary condition, which is Dirichlet and Neumann boundary condition. The important thing is that either at the boundary of the problem, either you have to specify a force boundary condition or a Dirichlet boundary condition or the kinematic boundary condition. So now so we can see that what is the application of this calculus of variation while finding out the this Euler-Lagrange equation. So we know, if we know the potential energy of the system now, so we can find out its governing differential equation. And in the finite element context, this has a very important aspect, which is variational formulation. So I will come to that variational formulation. So before coming to that, let me introduce one important aspect, is known as the delta operator. Delta operator. This is very simple. We need not to learn in detail here. So we write that variation of y in terms of y tilde and yx earlier. So this delta of y is actually the variation of y, or the variation of the optimal function given x. So the important thing is here that it is given x. So because y cannot be arbitrary, y has to follow some admissibility criteria, which is essentially the boundary condition. So now if you so this is nothing but the variation variation of y. So if you have a variation of y, then you will have a variation of f also. So suppose this is a variation of y, then what will be the variation of f, where my f is actually x, y, y prime. So what will be my del f? So essentially my del f will be del f by del y into dy plus del f by del y prime into dy prime. But look, don't confuse with the derivative, total derivative. For instance, the differential df is del f by del x into dx plus del f by del y into dx into dy plus del f by del y prime into dy prime. So the important thing is here that don't associate del f with the del x also. So here this is total differential, whether this quantity is not present in the variation of y. This is because the variation is allowable or admissible. Variation has to be admissible. So that's why this quantity, the dx, has to be 0 in the variation of y. So this concept I will explain. We will see this concept little bit more in the later days. So what we have till now we have learned is that we have a variation of a function which is this. Now this variation of this function can be written as delta of y, which is y prime and y prime minus yx, or y prime minus y, we can simply write. So y prime minus y. So this variation delta, this delta operator is commutative. So we all know what is commutative means. That is, if I just take, suppose if I take delta of y prime, then it is nothing but delta of dy dx. Okay, dy dx. So this is nothing but d dx of delta y, right? So this is the commutative property. Similarly, the integral of delta y dx is essentially delta of integral y dx. So this commutative property can be proved very easily. So I leave it for the homework. If you can't do it, I can explain it later. So now if I write my Euler-Lagrange equation that we have derived is in terms of these variations or the delta operator, it will be very handy. So the Euler-Lagrange equation was del f by del y prime or y minus d dx of del f by del y prime equals to 0. So this was my Euler-Lagrange equation. So how did I obtain that? I obtained that by I integral 0 to, or let me write it, x1 to x2. So f of y comma x y plus delta y comma y prime plus delta y prime dx, right? The way that I have derived in the previous class. So this is my I tilde. So I tilde minus I is essentially, now I'll call this variation of I, which is the first variation, in specifically the first variation of I, or first variation of the function. So that is has to be 0. So to do that, if I follow the same way, that what we did it earlier. So x1 to x2, that is essentially I have to take the derivative. So essentially del f by del y into del y plus del f by del y tilde into delta y prime. So now we are not using any tilde here. Look, we are just using variations of y. Now if I do it, which is x1 to x2, that is del f by del y into delta y plus I can write it del f by del y tilde into del f by del y prime into delta y prime. So this I can do integration by parts, that I did it in the last class. The similar way I can get this formula, that is x1 to x2, that is del f by del y in minus d dx of del f by del y prime into delta y dx plus del f by del y prime into delta y at x equals to x1 to x equals to x2. So now this is the same as the Euler-Lagrange equation that we obtained in the previous class, and this is the boundary condition. So what is the boundary conditions here? So either of this boundary condition has to be specified. So either del f by del y prime or delta y is given at x equals to x1, or del and del f by del y prime or delta y has to be given at x equals to x2. So this is the boundary condition. So you see, this is my boundary condition and this is my Euler-Lagrange equation. So how I get the Euler-Lagrange equation from here? Because the delta y, the variation can be arbitrary. So considering the arbitrariness of this variation, I can write that my Euler-Lagrange equation is df by del y f by del y minus d dx of del f by del y prime equals to 0 for any arbitrary value, for all arbitrary variation, but arbitrary variation has to be admissible. So this is the case, and one important thing is that this variation, this Euler-Lagrange equation for the functionals that we derived can also be involving the second derivative. For instance, if I have a function or functional of this form, that is of this form. So let us see functional of this form. So suppose I have a functional, right? So integral, suppose x1 to x2, and my functional is f of x, y, y prime, y double prime. So why I'm just doing double prime? Because if you have seen my earlier class we were discussing the beam problem. In the beam potential energy, we have that term, that is 0 to L EI by 2 d2w by dx2. This term was there, so curvature term, so this was there, so 0 to L q w dx. So this term was there. So in the beam problem, now That's why we need to find out what will be the Euler-Lagrange equation. The Euler-Lagrange equation is the same way that we did it. So I tilde we can do it in this way, that is integral x1 to x2, that is f of x comma y plus delta y prime plus delta y prime, y double prime plus delta y double prime. But yes, the differentiability requirement has increased, which is at least the approximation has to be the second order differential at least. So this thing now if I find out its Euler-Lagrange equation in the same way, we have to do 2 times the integration by parts. So that I will discuss in the next class, how if we have the higher order derivatives, how we can find out its Euler-Lagrange equation. So I stop here. So let us meet in the next class. Thank you.